Funding for this program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
I'd like to show you the most important piece of equipment that you're likely to encounter in a chemical laboratory. How much do you think it'll cost? Was it invented in the United States and made in Japan? Are you ready? Let's see. Here it is. This is it. Not a superconducting super collider, is it? Not a piece of equipment that's worth $100 million. Just a piece of paper, a chart, an idea, a tool for the mind. This was invented by Mendeleev, a Russian, 120 years ago. It's called the periodic table, and it's worth more to chemists than all of the pieces of equipment in our laboratories.
What are the properties of the substances in the world around us? There are two types of properties. Chemical properties refer to the element's ability to combine with other elements and form compounds. Physical properties include density, hardness, melting point, boiling point, and conductivity. Each element is different from every other element in its chemical and physical properties. This uniqueness can be traced to the atomic structure of the element. But some groups of elements also share common properties that vary systematically and predictably. These common properties are the basis of the modern periodic table. There are 109 elements in it. 88 occur naturally. The other 21 are man-made or artificial elements. For centuries, Latin was the common language of science, so many elements have Latin names. For instance, iron was ferrum, so its abbreviation became Fe. Gold was aurum, Latin for shining dawn, so it became Au. Madame Curie discovered an element and named it after her native Poland, polonium. And more recently discovered elements have been named after famous people, such as Einsteinium, named for Albert Einstein, and Nobelium, named for the man who established the Nobel Prize, Alfred Nobel. Besides a symbol for the element's name, in this case helium, each box also contains some important numbers. Notice the number below the He symbol. This is the atomic mass of the element, the total mass of the protons and neutrons. All helium nuclei contain 2 protons. However, the number of neutrons may vary. For example, there's a rare form of helium which has only 1 neutron in the nucleus. The 2 varieties of the same element are called isotopes. The atomic mass of an element is the weighted average of the masses of the isotopes in the naturally occurring element. The number over the symbol in each box is the atomic number of the element, the number of protons in each nucleus.
An atomic number is what determines an element's position in the table. The elements in the table are arranged in order of ascending atomic number as you go from left to right. Here we have hydrogen, number 1. Way over here, helium, number 2. Then lithium 3, beryllium 4, boron 5, and so on across to neon 10, back to sodium 11 and magnesium 12, and so on, left to right. Now there's another facet to the table. Because of the way it's laid out, each element is a member of a group that goes up and down the table and a period that goes across the table. For example, potassium. It is a member of this group, and it is a member of this period.
There are 7 horizontal periods running from left to right. Each one has been assigned a number, which is placed at the left of the period. 14 of the elements in periods 6 and 7 are pulled out of their place and laid out below. If they were placed in the table, it would look like this. So it makes it much easier to arrange the table if they are at the bottom.
There are also 18 vertical columns called groups or families. Each group is designated by a number and a letter, which is placed at the top of the column.
Elements within a family all have similar properties. To demonstrate this, let's look at one family on the far right of the periodic table, the noble gases.
These balloons contain the first 5 noble gases. We have helium, neon, argon, krypton, and xenon. Now we're missing radon because it's radioactive. We're all familiar with helium. It's used in balloons and blimps. The rest are used to fill various light bulbs and lamps. But what are some of the properties that they have in common? Well, they're odorless, and they're colorless, and they're all quite unreactive. And as you go down in the family, each one gets heavier than the previous one. Let me show you what I mean. This is helium. Here it goes. This is neon. It's somewhat lighter than air. There it goes. Now, argon and krypton are both heavier than air. And xenon is the heaviest of the ones we've seen. It's the proverbial lead balloon.
You can begin to see the different types of information that can be derived from the periodic table. But how do chemists use the table in their work? Glass making is one example. At one time in the ancient world, glass was so rare that it was prized more highly than jewels or gold. But as we mastered the techniques of glass working, glass became a commonplace necessity. The types of glass multiplied tremendously, so that today, glass comes in many forms and colors. Artists use it to create new and intriguing constructions. Craftsmen mold it by hand into the elegant forms of Steuben crystal. And factories manufacture glass for countless everyday uses. Basically, different types of glass are made by mixing silicon dioxide, sand, with different metal oxides, then melting them together. The choice of the oxides, which determines the characteristics of the glass, is guided by the periodic table. Dr. Jerry Fine is a glass chemist at the Corning Glass Works in Corning, New York.
I cannot imagine working without the periodic table because scientists are interested in looking for systematic relationships between different substances and between different elements. The periodic table is a simple way of looking up and finding systematic relationships between different elements that we can understand on a very simple level.
In the Glass Research Center at Corning, thousands of samples are poured each year as new types of glass are developed and perfected. One group of elements frequently used to make glass is on the far left of the periodic table, the alkali metals. By mixing in different alkali metals, glass with different characteristics can be produced. So understanding their variations in behavior is important to glassmakers, and indeed to all chemists.
We call this family the alkali metals. They make up group 1 in the periodic table. The first element is lithium, and then there's sodium and potassium. Down here is rubidium, and this one is cesium. Now, do you notice anything that they all have in common? You probably see that they're all stored in very unusual ways. And the reason we do this is because they're all highly reactive. I have here 3 containers of just water. Now, I'm going to take a piece of this lithium and put it into the water. Now, watch what happens. Oh, it starts to fizz a little bit. The fizzing now is the reaction of lithium with the water to produce hydrogen gas. Let's try the sodium. I'll get a small piece of that. Not too big because we don't want the reaction to be too violent. Oh, that reacts much faster, doesn't it? See the sodium bouncing around there again, fizzing, giving off that hydrogen gas. Okay, let's try potassium, the most reactive of the three. I'll get a small piece of that and put it into the water. Wow! That really reacted violently, huh? Did you see the immediate reaction of the potassium? Again, it formed that hydrogen gas, and the hydrogen gas was ignited.
So the alkali metals all have similar chemical properties, but they also vary systematically. As you go from the top to the bottom of the column, the atoms of each element become larger. Chemists can use this characteristic to increase the strength of their glass. The size of an atom increases as we go down any column. In the alkali metal group, the atomic size increases from lithium to sodium to potassium and so on. But as we move across a period, starting with an alkali metal, the size of the atom gets smaller and smaller until we get to a new period. Here we see a jump in atomic size in the next alkali metal, and again a decrease along the period. This pattern repeats itself throughout the table and is called periodicity.
Everyone is aware that glass tends to be a brittle material. If you've ever thrown a baseball through a window, you know that the glass breaks quite readily. However, there are ways of taking that simple window glass, which is made of sodium, calcium, and silicon, and treating the glass to make it strong. One way we do that is by use of the periodic table. If we take that glass that contains sodium and substitute potassium in the surface for the sodium, or substitute an element that behaves basically in the same way, but is slightly larger, we can enhance the strength of that glass and make strong glass.
The results of this process are quite easy to demonstrate. If a steel ball bearing is dropped from 1 foot onto glass made with the alkali metal sodium, watch what happens. The sodium-based glass shatters completely. Now watch what happens if the same ball bearing is dropped on a piece of glass where potassium has been substituted for sodium. This time, the ball will be dropped from 20 feet.
The way we do that is by taking the glass which contains sodium and dipping it in a bath containing molten potassium. What happens is the molten potassium substitutes for the sodium in the glass on the surface of the glass. Because from the periodic table we can tell that potassium is larger than sodium, the potassium atom literally stuffs the surface of that glass.
The predictive ability of the periodic table was first demonstrated by a Russian chemist, Dmitry Mendeleev. 100 years ago, he developed the predecessor of our modern table. Mendeleev's table included all the elements then known and was consistent with their varying properties. For 3 undiscovered elements, he left blank spaces, predicting that they did exist and that their properties would be consistent with their position in the table. For his time, it was an amazing hypothesis. One position that he left blank was this one for gallium. Based on the properties of the 2 neighboring elements, aluminum and indium, Mendeleev was able to predict some of the properties of gallium. He was also able to predict 2 other elements, germanium and scandium. When the elements were discovered and their properties measured, Mendeleev's predictions were found to be remarkably accurate. In this century, another chemist, an American, rearranged the structure of the table based on the properties of elements that he himself had discovered. His name is Glenn Seaborg. In 1944, the periodic table didn't look like it does today. The periods and groups were laid out differently.
Back in the days of Mendeleev and actually extending into the 1930s, the heaviest elements, thorium, protactinium, and uranium, were put into the periodic table up in the body of the periodic table under hafnium and tantalum and tungsten. And it was my idea in 1944, while I was working on the at the metallurgical laboratory in Chicago on the Manhattan atomic bomb project, that these might be misplaced and that they might be the first three members of the actinide series. And then I boldly, and against the advice of some of my eminent inorganic chemist friends, plucked those out of the body of the periodic table and put them in the row below, and then continued that with 93, 94, and so forth, up to 103.
The idea to rearrange the table occurred to Seaborg late one Friday afternoon. He was drafting a classified report for a seminar the following Monday, and he decided to include this idea in his report.
I presented this at that Monday seminar, and it, you know, it went over like a lead balloon. You know, the idea that one would be brash enough to change the periodic table after all these years in this fashion, when that, you know, everybody felt that thorium, protactinium, and uranium should be in those sacrosanct positions up in the body of the periodic table under hafnium, tantalum, and tungsten.
His discoveries of the new elements remained classified until after World War II. When he was able to publish, he incorporated his new arrangement of the periodic table.
I showed this periodic table to some of my friends, the most eminent inorganic chemists in the world, and told them that I planned to publish it, and they said, "Don't do it, Glenn. It's wrong. It will ruin your scientific reputation." Well, I'm fond of saying that I had an advantage. I didn't have any scientific reputation at that time, so I went ahead and published it.
Seaborg's new arrangement enabled him to predict the properties of still more elements. His ideas were later verified when the elements were produced artificially. Seaborg was awarded the Nobel Prize in Chemistry in 1951. His rearrangement is our modern periodic table, and what ultimately determines the position of an element in this modern table is the way the electrons are arranged in the energy levels of the atom. As we move through the table and the number of electrons in an atom increases, the energy level diagrams contain more and more levels and sublevels. Both the number and types of electron clouds increase in complexity. For example, this is the energy level diagram for hydrogen's 1 electron in an S cloud called the 1s. Lithium's 3 electrons are diagrammed like this, 2 electrons in the 1s cloud. Each cloud can contain 2 electrons. Then the 3rd electron is in another cloud, an S cloud at the 2nd level. Let's move forward to sodium and look at an energy diagram for its 11 electrons. Its first 2 electrons are in the cloud at the 1s level. Its next 2 electrons are in an S cloud at the 2nd level. This is actually only the first of 2 sublevels at the 2nd level, so it's called the 2s sublevel. The next 6 electrons of sodium are in the other sublevel, called the 2p sublevel. Notice the number of clouds in the 2p sublevel. There are 3 p-shaped clouds in it. Each of these clouds contains 2 electrons. Where does sodium's 11th electron go? As we move higher on this energy diagram, we encounter the first sublevel of level 3, the 3s. It has only 1 s orbital in it. Sodium's 11th electron goes here. When chemists diagram energy levels of electrons within an atom, they replace the figures of the clouds or orbitals with blank lines. Arrows are used to indicate the presence of electrons in each orbital. This is the diagram for sodium's 11 electrons. Sodium is the 2nd alkali metal. Note that it has 1 electron in its outer orbital, the 3s. This is the diagram for lithium, the 1st alkali metal. Look at its highest energy level. Once again, it is only half filled with only 1 electron in the 2s sublevel. The similarities and properties of lithium and sodium, and indeed all the alkali metals, are due to the similarities in their outer electron structure. The outer electrons in any atom are called its valence electrons. The noble gases are another example of a similarity in outer electron structure. They have a filled S or P sublevel, a very stable arrangement. Next to them is an important group called the halogens. They are all missing an electron from an almost filled sublevel, which makes them very reactive. Now, as the number of electrons in an atom increases, what are the rules these electrons follow in filling different sublevels and orbitals? To find out, Don Showalter went to St. Albans School on the grounds of the National Cathedral in Washington, D.C.
We're out here today to show you how the electrons fill up the various energy levels that you just saw in that diagram. And to help us out, we have these 11 baseball players.
Right, Coach!
All right. These baseball players are now going to represent electrons. And we're going to have an electron practice. They're going to practice the rules that chemists use to fill the various energy levels. Now, here's the ground rules. These bleachers represent the various energy levels. The lowest one being the 1s, colored blue.
1s!
Good. The next energy level is the 2s. It's colored green.
2s!
All right. Now, the 2p has 3 sublevels, and it's colored red.
2p with 3 sublevels.
Good. And we've got the highest energy level is the 3s, and it's colored yellow.
3s!
All right. Now, there are 3 basic rules that we have to follow. Rule number 1. Electrons fill lowest energy level first.
Electrons fill the lowest energy level first.
Okay, here's rule number 2. No more than 2 electrons in any one orbital.
No more than 2 electrons in one orbital.
Beautiful. Here's rule number 3. If you have more than 1 orbital in a sublevel.
If we have more than 1 orbital in a sublevel.
1 electron in each orbital before you double up.
1 electron in each orbital before you double up.
Great. Have you got it?
Yes, Coach!
All right, let's get energized. The first element is hydrogen. Go!
Hydrogen has 1 electron, so it goes in the lowest energy level available, the 1s.
Now we're going to skip to nitrogen. Go!
Nitrogen has 7 electrons. The first 4 fill up the 1s and the 2s. But what about the next 3? 1 goes in each of the 3 2p orbitals.
Now we'll skip ahead to sodium. Are you ready, team?
Yes, Coach!
Go!
Sodium has 11 electrons.
Go!
The first 4 go into the 1s and the 2s. The next 3 go into each of the 2p orbitals. Then numbers 8, 9, and 10 go in. Finally, the 11th electron goes into the 3s sublevel.
And that's the way the electrons fill the energy levels. Right, team?
Right, Coach!
Scientists at the Smithsonian Museum have applied a technique that uses information about the energy levels of different atoms to study works of art. This technique analyzes the elements in different pigments and is called X-ray fluorescence. Jacqueline Olin is a chemist at the Smithsonian.
If, for example, you were to know an artist's work so very, very well that you knew that that particular artist never used a particular pigment in all the paintings that have been studied, and there's a painting in question, one might analyze a painting to determine whether or not that pigment, a pigment that's not characteristic of that artist, is present.
X-ray fluorescence involves bombarding the atoms in the painting with X-rays, causing them to eject an electron. To see exactly how this happens, let's return to the electron team. Here are the electrons in their energy levels for the element sodium. As an X-ray enters the atom, it knocks out an electron in the lowest orbital, the 1s. When this happens, some of the electrons in higher energy levels fall to lower energy levels, filling the gaps. As the electrons cascade down to lower energy levels, they give off an X-ray pattern that is characteristic of each element. Instruments analyze these X-rays and identify what element is present.
It's very nice to be able to quickly and easily find out what some of the elements are that are in the painting, because we have looked at the painting in terms of the colors we see, and we'd be interested to know if that blue is a copper-containing blue or a cobalt-containing blue, and that can be done readily by using X-ray fluorescence to identify the elements present in that area. So it's a nice technique for non-destructively and quickly identifying some of the elements present in the painting.
To review, the elements in the periodic table are arranged in serial order according to their atomic number. The rows are called periods and the columns are called groups. The size of the atoms increases as we go down in a group and decreases as we go across any period. This is an example of a periodic property. Elements in any group have similar arrangements of electrons in their energy levels. Therefore, they have similar chemical properties.
You can see right away that a given electronic configuration implies similar properties. For instance, the alkali metals with their one electron in an S subshell, they all readily give up that electron and no more than one electron. And all of the halogens on the other side of the periodic table with their missing electron in a p subshell readily accept such an electron. One might ask, why do we concentrate on the outermost electrons and not all the other ones? It's because the outermost electrons are at highest energy. They're furthest away from the nucleus. In them is chemistry.
Funding for this program was provided by the Annenberg CPB project.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And